Hi everybody. So just as requested, I'm putting the performance final review on YouTube for you guys to have a video. So one of the key things is you know that your performance final is next Tuesday. So that's on Tuesday, December, let's see, what's next Tuesday's date? Tuesday, December 12th is when it will be. And this will be a DBQ, which remember stands for document-based question, that covers material that we've been talking about all semester, and will be in similar style to gateways and DBQs in the past. So let's talk about a few steps to write an awesome DBQ, because this DBQ will be 5% of your entire grade and can replace poorly written DBQs from before. So it really needs to be the best DBQ you've ever written for my class. So the first thing you're going to want to do is read the whole thing when you get it 2 times. Okay? Read it 1 time just to get a general overview, and the second time you want to make sure that you go back and you're looking for details. And when you are looking for those details, I want you to underline your chemistry vocabulary. Okay? Now, the reason why you're going to do this is because step number 3 is to take at least 4 of those words and define them. Okay, or describe them. And so when you see this, it's just going to be kind of like off in the margins because you can write all over it. And then the fourth thing is you're really going to want to analyze your bullet points. So for each of those bullets, okay, what you're going to need to do is you're going to need to decide which document to use, or documents. You can use plural. You can use plural. You can use more than one. And then you need to answer the question. So if it asks you, okay, what is a flame test lab? What is ionic compound? What is electron configuration? What is a valence electron? What are the periodic table trends? Like any of those things, you need to just kind of answer off to the side in short little descriptions. And so when you're writing these bullet points, one of the key things is that you have to cite your document. Okay. Now, when we're talking about citing documents, okay, many of you are getting pretty good at actually remembering to do that, but not very many of you are remembering how to do it correctly. So there are 2 of the main ways for you to cite a document, and so I want to go over them. For example, you might say, as seen on the periodic table, in document A. All right, so this is where you're kind of referencing the document in your sentence. Chlorine is further to the right than hydrogen. Okay, now this sentence has 2 key points. First of all, is it says in document A, specifically what it is. It even gave a title to document A, the periodic table. And also this part, chlorine is further to the right. Okay, this is something that you can see with your own eyes. Okay, if you cannot see something, a symbol or a picture or a word on the document, then you should not be citing your document at that time. So for example, even because chlorine is further to the right, that means it is more electronegative than hydrogen. However, if you were to say, as seen on the periodic table in document A, chlorine is more electronegative than hydrogen, then that would be an inappropriate way to cite document A, because the periodic table doesn't tell you that chlorine is more electronegative than hydrogen. What it does tell you is the position of chlorine on the periodic table compared to hydrogen's position, and then you know based on vocabulary and things like that from class what that means. So the what does that mean, what you see, is reasoning. So remember, when you have a claim, evidence, and reasoning, the evidence part has to be what you see in the document. It cannot be what you know because of what you see. And so the second way that we can cite this document is by saying chlorine is further to the right side of the periodic table than hydrogen. Now that's exactly what I just said, but I didn't say in document A, and what I'm just going to do is I'm going to put document A in parentheses at the end of my sentence, and that implies that where I got this information or how I know this evidence is based on looking at document A. So let's go over the next part. So that's just like kind of broad overview ideas of the things that we need to talk about in reference to DBQs in general. So starting the DBQs, doing some brainstorming, things like that, and then also remembering how to cite our documents appropriately in our writing. Okay. Now, specifically in class, our DBQs have always been associated with labs, and one concept that really combines a lot of different things is when we're talking about ionic and covalent compounds in reference to periodic tables and polarity and valence electrons and safety and labs and things like that. So we want to just do a big, broad overview of ionic compounds versus covalent compounds. Okay, so this DBQ could ask you anything and everything about everything since August. So this one topic really does hit on a lot of those things. A lot of themes come together and connect in this unit. So one thing to remember is that ionic compounds are made up of metals and nonmetals and polyatomic ions. Okay, now one way to know where metals and nonmetals are is if you have your periodic table of elements, okay, there is a staircase on them. Anything to the right, or excuse me, to the left is a metal, and anything to the right is a nonmetal. And on the back of your periodic table, it has polyatomic ions like PO4 with a -2 charge, or CO3 with a -2 charge. Oh, and phosphate has -3. Okay, all of these are polyatomic ions because you have many atoms that are combined together into one ion that acts as a unit. Okay, and so covalent compounds are bonds between nonmetals only, although occasionally you might have a metalloid, which are the elements that are along the staircase. But remember that aluminum, which is on the staircase, is a metal. It is the exception to that rule. Now, one key thing about the way ionic compounds and covalent compounds differ, and the reason why they differ, is how their electrons are used in bonding. Okay, so when we're talking about ionic compounds, the key thing there is that your electrons are transferred during bonding. So we're just going to, electrons are transferred specifically from the metal to the nonmetal for bonding. Okay, so what that might look like is if I have magnesium and oxygen. We know that magnesium is in column 2 of the periodic table, which tells us there are 2 valence electrons. And guys, I know magnesium has 2 valence electrons because I see it's in column 2 in the periodic table. That's another place where anytime you're using the periodic table to figure out information, that's a place where you can cite the periodic table as a document. Okay. Now with oxygen, oxygen is in column 16, so it has 6 valence electrons. So I'm going to put 6 dots around oxygen. Now, the reason why this is important is because of the octet rule. Okay, remember, atoms are going to gain or lose electrons to have 8 valence electrons available. Okay, and when magnesium loses those 2 electrons, it has 8 on the shell underneath it in order to have that 8 valence electrons. So really, you're going for either 0 valence electrons, like 0 of the original, or however many you had plus a few more to get to 8. And so with electrons being transferred, what's going to happen is magnesium has 2, oxygen has 6. Magnesium is going to give oxygen its 2 valence electrons. And when it does that, magnesium will have a +2 charge. It's positive that it lost those electrons, and so that makes it a cation. And then oxygen will have gained 2 electrons, so we now have 8 total electrons for a -2 charge. And because it's negative, it is an anion. And those charges are what force them to be attracted to each other and have that ionic bond. So the attraction between positives and negatives creates the ionic bond. Okay, now when we're talking about covalent compounds, electrons move in a slightly different way. And what I mean by that is that, which we're going to come back up here to this, is that electrons are shared to create bonds in covalent compounds. Now, this is important because of several different reasons, because not all the time are electrons shared equally. Okay, when you have a polar covalent compound, right, this is when you have electrons are shared unequally. Right, it's like when you let your sister have the computer for 20 minutes, but you get it for 2 hours. And the reason why this occurs is because the more electronegative the atom, the stronger it is. So if you have an unbalance, then it means that they're not going to be able to share. One will be stronger than the other. So in terms of pulling the electrons towards one another. So if I am looking again at my periodic table, which I'm going to draw over on top of it this time, if I have something like hydrogen and chlorine, okay, hydrogen and chlorine are on opposite ends of the periodic table. And the way the trends work is as you go up the periodic table, you are more electronegative. So hydrogen is going to be more electronegative than, let's say, francium, which is down at the bottom. However, if we're looking side to side, okay, it's going to increase as you go across the periodic table. So therefore, chlorine would be more electronegative than hydrogen. And so when you have a polar covalent bond, that means that the differences between their 2 electronegativities are great enough that one has the electrons more often near their nucleus than the other atom. They are the bully. Now, that is not always the case. You can have something that is going to be nonpolar covalent. And when you have a nonpolar covalent compound, this is when electrons are shared equally. This is most common when the atoms in a bond are the exact same element. So if we are talking about some examples, okay, the way you're going to see covalent bonds in pictures or Lewis structures like we saw for magnesium oxide is an example might be if we have chlorine, which chlorine is one of the 7 diatomic molecules, so it always covalently bonds with another one. This is a single bond. Okay, now a single bond represented by this line in the center is contains of 2 valence electrons. Okay, now something like oxygen, again a diatomic gas, has what we call a double bond in the center, okay, connecting the 2 atoms, and it has 4 valence electrons. Nitrogen, again a diatomic molecule, has 3 bonds in the center, which are triple bonds, and it has 6 valence electrons. Okay, and the more bonds there are, the stronger it is. So a triple bond is going to be stronger than a single bond. And when we're looking at these things, the key thing to know is that every single one of these has the same element on either side of the bonds. When this is the case, you have the same element. That means you have the same electronegativity values, which I'm abbreviating as En, which means the difference in those, so your delta electronegativity is going to be equal to 0. And when you have a delta electronegativity difference equal to 0, meaning the difference in their strength to attract electrons is the same, there's no difference, this would be a non-polar covalent compound. And we know it's covalent because all of these molecules, or all these atoms, excuse me, are nonmetals. They're located on the right of the staircase on the periodic table. But we know, you say, Miss Nichols, you also just said that there was something that was polar covalent. So let's look at what a polar covalent compound might look like and how we might be able to tell. If we look at something like HCl, hydrogen chloride, well, actually it's hydrochloric acid, but we haven't gotten to naming acids yet. So if we look at this, and again, we're looking at our periodic table that we drew before. We know hydrogen is on the left, chlorine is on the right, and so what that means is chlorine is a very highly electronegative, okay, whereas hydrogen is a lower electronegativity value. They're spread far apart, and so when you see this, okay, that big difference, this will be a polar covalent molecule. Now, if you're given the actual numbers for these, I believe chlorine is like 3.5 and hydrogen is 2.1, and so if you were to actually do the electronegativity difference and said 3.5 minus 2.1, you would get 1.4, which in class we discussed the range for all of these things. We know that for an ionic compound, you have to have a delta electronegativity difference greater than or equal to 1.7, but for polar covalent, your delta electronegativity value needed to be less than 1.7, but it had to be greater than or equal to 0.4, which is exactly where our delta electronegativity value for HCl falls into place. And to be non-polar covalent, your delta electronegativity value had to be less than 0.4. Now, you can use these values in this range to decide whether or not something will be polar covalent, but if you are not given these numbers right here, which you have to be given in order to use them, there's no way you would just have them memorized. Well, I do, but it's because we've done these same problems over and over again in class. You would need to use their positions on the periodic table in order to really figure that out. So ionic bonds and covalent bonds, again, are different because of all of those regions. And so like a way that you might say this is we might say because chlorine is on the right and hydrogen is on the left, there's a big difference in electronegativity, and so we have a polar covalent compound. Okay. Now, these are all the chemical ways that ionic and covalent compounds are different, but if we want to talk about physical properties too, because we know that there are, again, a lot of differences between these things. So if we talk about some of the big physical properties, we talk about how ionic compounds have a high melting point, okay, whereas covalent compounds have a low melting point, which is not all that surprising because we know that ionic compounds include metals, and a property of a metal is having a high melting point, whereas covalent compounds are all nonmetals, and nonmetals have low melting points. But the key thing that we want to know is why do they have these properties? And the reason why is all down to their intermolecular forces. So the intermolecular forces for an ionic compounds, so intermolecular forces, which are often abbreviated as IMFs, are very strong for ionic compounds. Now, the reason why they're very strong is, let's take magnesium oxide again as an example. Let's say I have an atom of magnesium oxide ion, okay, and it's next to an oxide ion, anion. Okay, well, there's going to be this attraction between this positive and negative charge, but we know that you don't only have one formula unit or one unit of magnesium oxide in any given sample. You're going to have millions of these formula units. And so what if it's got neighbors? What if there's, on the other side of that oxygen, there's another magnesium ion and another oxygen ion, and underneath it, again, oxygen ions and magnesium ions and even more and more, and it just keeps repeating. Well, who's to say that this magnesium here that we drew originally has to be attracted to the one on the right? Why can't its positive charge also be equally attracted to that one? And then you start to realize, oh man, there is a repeating unit here, and those attractions are so strong that the energy required to break those forces and separate them apart to melt them also has to be extremely high. Okay, our temperature measures the amount of energy. The higher the temperature, the higher the amount of energy required to break these intermolecular forces. Now, while that does sound a little complicated, one thing to note is that ionic forces are the strongest. That's why they are the highest melting point. And covalent compounds, as we are now used to, are going to be a little more complicated. They have lower melting points, and this is because their intermolecular forces are weaker. Okay, not to say that they are not strong, or they don't have strong characteristics, but in general they are weaker than ionic compounds. Now, there are three intermolecular forces that are really related to covalent compounds. The first one that we're going to talk about is London dispersion forces. And London dispersion forces, often abbreviated as LDF, are the weakest, okay, and out of all of them. And they are also, in order to have London dispersion forces, you can be polar covalent and nonpolar. They are in everything. And the way that they become stronger is if they have more electrons than something else you're comparing them to. Whichever one has the larger amount of electrons is going to be the stronger London dispersion force. The next type that we're going to talk about is dipole-dipole forces. Okay, so dipole-dipole forces are when you're talking about permanent polarity. Okay, so permanent polarity, because when you have permanent polarity, it gives partial charges. So again, if we go back to our original compound that we keep coming back to, HCl, because chlorine is more electronegative, what happens is it gives chlorine a partial negative charge and hydrogen a partial positive charge. It's not fully positive and fully negative, but it is there. And so that permanent attraction or that permanent charge is going to give it a pretty strong attraction to the other opposite charges in neighboring molecules. And so that means in order to have that permanent polarity, you need to be a polar covalent compound. Okay, you can't be nonpolar and have permanent polarity. That just doesn't make sense. Okay, now the third type is a type of dipole-dipole force that we call hydrogen bonding. Okay, again, it's going to be about permanent polarity. However, the difference is the types of atoms that are going to be involved. When you have hydrogen bonding, okay, it has to be polar covalent, and it has to be between hydrogen and either fluorine or oxygen or nitrogen. You know, the 80s song, Girls Just Want to Have Fun? Well, I just like to say hydrogen just wants to have fun. It's got to have fluorine or oxygen or nitrogen. And the reason why this works is because if you have a water molecule, for example, water is going to be a polar covalent molecule, and this is what the Lewis structure for it looks like. We know that oxygen is more electronegative than hydrogen, so it's going to have a partial positive charge, and oxygen is going to have a partial negative charge in all of these. So what happens is, let's say there's a neighboring molecule. You have another water molecule nearby. Well, again, this water molecule is also polar. Okay, so it's got a partial positives on the hydrogen and a partial negative on the oxygen. Well, even though we have this polar covalent bond between the oxygen and hydrogen within it as an intramolecular force, we're also going to have this intermolecular force where the hydrogen that's partially positive is going to be attracted to the oxygen in a neighboring molecule that's partially negative. And so that will create a force weaker than the polar covalent bond found in the actual molecule, but still an extremely strong bond. And so when we're looking at the strength of these, if we want to label not only our covalent compounds, but also ionic forces, we know that ionics are going to be number 1, hydrogen bonding is number 2, dipole-dipole is number 3, and London dispersion forces are number 4 at the weakest. So these are going to be how, you know, the more bonds it has, the stronger the bonds it has, the higher the melting point. So let's talk about other physical features of ionic versus covalent. And the main thing that I really just want to say is that ionic compounds are highly conductive when dissolved in water. So when dissolved in water, whereas covalent compounds have low conductivity when dissolved in water. Okay, now the reason for this is because in a covalent compound, like let's just say we have a carbon-hydrogen chain that has covalent bonds in it. If we have this molecule, there's no charges, there's no ions, there's no positives and negatives, things like that. Even if it was polar, it's not fully positive or fully negative. And so it doesn't leave room for extra electrons to kind of come in and get carried throughout the solution. Whereas when you have something like magnesium oxide, where you've got these oxygens that have a lot of extra electrons, but you have these magnesiums that are missing some. Well, magnesium has no problem taking an electron and then passing it on to its neighbor. Okay, so that's why that is pretty easy for them. Now, this is part one of your performance funnel review. This video is about 31 minutes, so I'm gonna stop it there. But please, please, please keep this in mind and then go to the next video for part two.